Okay, this is forces. You guys can still see this, right? The blanks. Good. All right, so this is roughly day 6, day 5, day 6. Okay, so we're gonna take a look at the Atwood pulley problem, or basically a pulley that has a mass on each side of it, and it's going up and down in either direction. Okay, so this is the for this guy Atwood. So we have this pulley here, and say it's attached to a ceiling.
Mr. Kelly, it's still the game plan screen for me.
Yeah, you're on the Word document.
Okay, yeah, it's about to time out, so 1 second. All right, sorry about that. All right, you guys see this now?
It's visible.
The pulley problem?
Yeah.
Okay, so let's say that we have a pulley attached to the ceiling, and then we have, so we have a mass on this side. Let's call it, a 5 kilogram mass. And then on this side, we have a 4 kilogram block. Now this time we're going to have 2 tensions. So we have this tension in the string here, and then we have a 2 kilogram block here. Since 6 is bigger than 5, the acceleration of the system is going to be, be something like this. It's going to go up, over, and down this way on the right side. So now the tension in the string is always going to be, by definition, or what we've talked before, the tension in the string is always going to be going towards the pulley in this case, because that's the source of the tension. It's going upward. And as that tension is going up to the pulley on both ends here for the same string, that's going to be balanced by the weight of the blocks coming down. So the tension going up is going to be balanced by the weight coming down on both sides. So we have 2 strings this time, so we'll call them T1, and then this is going to be tension T2. So before we do anything or get confused with anything, hopefully, what we want to do is just draw a free body diagram everywhere. We want to draw a free body diagram on all the blocks with all of the tensions. And go from there. So our perspective is going to be the XY plane. There is nothing happening in the X plane because it's all vertical. So the pulley system is going to cause the 5 kilogram block to move up as the 4 and the 2 go down, since this is a heavier weight than the 5. 60 newtons roughly, as opposed to 50 over here. So it accelerates up and down. So again, let's draw the perspective. This is our X, Y perspective. We know that the Y-axis will be straight up and down this time because it's hanging exactly vertically. It's not on a ramp or anything. And there's no X component because nothing's happening horizontally. So perspective, picture, perspective. Now let's get a free body diagram for each. for each mass. Okay. So you guys okay with the fact that tension is always going to be pointing towards the pulley? It's always going to be pointing up as the weight comes back down to keep it attached. So we have the, let's say we have the 5 kilogram mass here. And this is going to be T1 coming up to the pulley. And this is going to be negative FG, which is equal to negative M1G. And then, so for the 4 kilogram mass, you have negative T1. And why is that? Because, get to him in a second, I guess. So the acceleration of the system is going to be going up and down, up from the left and down to the right, on the right. All vectors moving in the same direction as the acceleration are going to be positive vectors, and all those moving against it, in this case, will be negative. So not only that, but intuitively, we know that the force of gravity, which is a vector, points down, so that's going to be negative in that sense as well. But in the context of this problem, it's going to be negative with respect to the acceleration of the system. So here we will have 2 forces on the 4 kilogram mass. We have a tension called T2, it's the second string. It's moving with the acceleration of the system, so it's going to be positive. And then I'm going to call this mass 2 for the mass in the system. That's going to be positive because that moves in the direction of the acceleration of the system. Moves like this, acceleration down. And then also, oops, keep the colors consistent. So we have the 2 kilogram mass, which has a tension by the second string. And since it goes opposite the acceleration, it's going to be negative T2. And then this force down here, the weight of the 2 kilogram mass, I'm just going to call him M3G for the third mass. And he's also moving downward. The acceleration is downward with respect to the 2 kilogram mass as well. So therefore we have M3G, which is positive, which moves in the same direction as the acceleration of the system. And T2 is opposite the acceleration of the system. That's why it's negative. So there's nothing to the question. I mean, if there's anything that you're not intrinsically seeing, please ask, obviously, always, but tension is always going, I mean, it's always going to be going to generally away from the object to a source like a ceiling or a pulley or somebody, you know, pulling the system. So tension is pretty much always away from the object. Like here, T2 will be going towards this 2 kilogram mass with respect to the 4 kilogram mass because the 2 kilogram mass is pulling the string away from 4, opposed to the tension here is being pulled away by the 4 kilogram mass up top. So it's always, the tension is always away from the object to some other source. No, not generally, because tension by definition is tight. So when you push something, it's not a tension. That's something else entirely. So in overall context, we can keep things simple and say tension is always going to be a pulling away. So, I mean, let's try. I mean, with practice, we'll try not to get into the trivial vagaries of the wording because that in itself can be a nightmare. You know, we don't want to cause ourselves any more headache than we need to. So tension is, just think of it's always something that's going to be tight, tense. You're tense, you're tight. Right? So it's some other source away from the object that's pulling. Okay. Those are the free body diagrams, and now we're going to go to the equations. Oh, well, our object is to find the acceleration of the system, just like we did in the other examples, as well as the tensions in the strings. And that's basically the prototype for the skills test. You're going to have an Atwood Pulley system, a little bit jazzed up, but you know, the thing about physics is it's going to be cookie cutter. Like, you're not going to get the same problem with different numbers. That's cheesy. The thing that you want to do in physics is to make sure that you have the logic down so that when the problems do change a little bit, you recognize the style, you recognize the type of problem, even though it's souped up, you know how to attack it logically. All right, so it might take a little bit more work, a little bit more time, maybe some nuanced reasoning. That's where your resolve comes in. That's where your willingness to practice comes in. That's where you want to read the text again. That's where you want to read over your notes and keep getting after it, because it's just not a cookie cutter type of deal. But so the goal that I will do for you, obviously, is to show you the logic, explain the logic, and we'll have at it. Hopefully, with enough time and enough practice, we will become very good. So that's the point there. Okay, so we have our free bodies. Now let's go to our equations, which was a method, perspective, free bodies, equations. Let's solve. All right, so next, step 3, if we will, is to get our equations of motion. Okay. So we know it's going to be a system, and everything is in the y-axis. Nothing's moving horizontally, just a vertical pulley system. And so for the first mass, which is the 5 kilogram mass, I'm going to just say all of the forces in the y-axis for the first mass are going to look like this. T1 minus M1G equals M1A. The whole system is moving. There is no situation where there's not going to be a net force. So everything's going to have MA, M1A, M2A, M3A. And it's a whole system. So we're going to add these guys together because they move as one. They move with one uniform acceleration, even though there's different tensions, there's different masses. Gravity is obviously the same. So we have negative T1 plus T2 for the second mass, because T2 is moving with the acceleration. And then we also add the weight of the second mass, and that's going to be equal to M2A. All the forces for the second mass add up to mass times acceleration for itself. So M2A, just like we had M1A up top. And for the third mass, so we have a third equation here. And so that, according to our free body diagram, will have negative T2, as we see there, and plus M3G. So you can see the power of the free body diagrams done accurately creates our equations. Negative T2 plus M3G equals M3A, and you're ready to go. The system of equations adds up to a net force. Net or total equals, for that, you can see how this makes life easier. Now, one way to do this problem, you can have separate equations hanging out all over the place, so just put them all together and you can see the cancellations. You see that this is a system. This helps you understand or appreciate, hopefully, that this works together as unity. Yep, it's accelerating, yep. And the thing is, this is why the power of demonstration is important. Can be in class, but usually would have a demonstration to show, hey, this part is gonna pull down as this guy pulls up. Whole thing is accelerating. Okay, so before I do all that, so we can see that these tensions can't cancel out. T2, life easier. And so it just comes out to be negative M1G plus M2G plus M3G equals A is distributed, so I'm just going to say A M1 plus M2 plus M3, because it's going to be M1A plus M2A plus M3A, so distribute out the A's, and it's equal to A times all the masses. Solve for the acceleration. Easy, right? I hope you can get to this point. Is there any questions at all? Do not be doubtful anywhere, because it's not about what equation do I use, it's why. It's always why. Because you get into that whole thing about, should I use this, or what do I need to put here? Now you're going to be in the weeds, okay? So you want to know why. Yeah, and even gravity, the G's distribute, so negative M1 plus M2 plus M3 equals all of this, A. And you're gonna want to solve for A. And we use 9.81 and 9.8. It doesn't really matter because they're not worried about sig figs. The question was, do we use 9.81 and 9.8? I mean, again, that's trivial. Thankfully, physicists are, when necessary, you know, it's like, yeah, we're going to use it if we're really trying to be precise. Like, if we're trying to send a shuttle to Mars, we better get our sig figs right. But in just approximating things, it's okay. Because there was a sig fig issue one year and for one mission, and totally lost the rocket. The mission, I think they were trying to go to Mars, put satellite in orbit around Mars, and I think the ESA, the European Space Agency, and NASA, they were using two different units. It wasn't even sig figs. One was using the English system, one used the metric system. Why was that going on? Don't know. But that cost a mission. All right, so let's go and solve this out. Solving for A, and then we divide everything by the total mass. Right, because we're solving for A, so we divide both sides by M1, M2, M3. It's the numerator, and now we just put in the numbers. So 9.8 or 9.81. -5, right? Plus 4 kilograms, plus 2 kilograms. I wrote 3 there. Doesn't really matter, but keep the numbers consistent. Okay, so 5 plus 4 plus 2. And we'll have -1 plus 2. There's -9.8. Divide that by 11. That's going to be our acceleration. Oh, this +1. Sorry. So that's nope. -1 plus yeah, positive. Okay. So that's the acceleration of the system. So 0.89 meters per second squared, and that's in conformity to our convention that we're going to choose positive acceleration. The system is going to always go in the direction of positive acceleration as opposed to some negative. Keeping everything, if we did have an x-axis, we would have acceleration along the positive x-axis. So everything's pretty consistent here. It should come out to be positive. It is accelerating. It is speeding up. It's not going to be negative, which would indicate a deceleration, some friction in the system. Okay, so that's 0.89, and then we can get the tensions. Okay, just back substitute. So we can just take one of the equations. So take the first equation, T1 minus M1G. Have T1 equals. Okay, so that's going to be 5 times 0.89 plus 9.8. I just distributed the masses. This is algebra. Please don't get confused by that. Right? I just did M1 A plus G.
Can you scroll up for just a second?
Yeah. Where?
Just the end of the calculations for acceleration.
Okay.
A little bit farther up, please. Thank you. Sorry.
No problem. I want to know what you didn't see. Okay. All right. So, got that part?
Yeah, thank you.
All right. So then, yeah, I just add that and multiply by 5. So that's 53.45 newtons. I think the actual problem had 3 kilograms opposed to 2, but that's all right. This is an example. So that's the tension in the string for T1. I'll come back there. Again, T1 going up here and up here, it's going to be 53.45 45 both ways. It's the same string. So uniform. And then T2, let's see, we can choose any one of these. We choose the last one because we have to deal with T1 again. So we can look at the last equation. So we negative T2 plus M3G equals M3A. Let's put T2 on the other side, and then we'll just have M3G minus M3A. Just do a swap like that. M3 distributed. And that will be 2, 9.8 minus 0.89. Times 2, 17.82. For the second tension. And that's all you really do. Have some time to talk about it. Any questions on it? Any parts you missed? But this is the logic. This is the, what you want to do for skills test tomorrow. You want to follow the logical steps. Take a look over that. And if you have any questions, we can talk about it. Okay. No friction problems, just the pulley problem like this one. Yeah. So this is why I wanted to do, this is perfect because good thing I was, whether we had the abbreviated class or not, it was going to be it would probably been another type of problem, but glad we have an extra day. That's why meeting every day is important. But yes, it'll be a pulley problem tomorrow. My channel is Dark Stack. Don't ask. It's my pirate name from back in 2008. Because back in 2008, I didn't plan on having I just made the channel. I just abandoned it. Stayed around. Okay. Yeah. And then I'll be putting up all the lectures, within a day. Of course. Yeah. Try to get them up as soon as possible. Any questions from start to finish? We can, go back, have some time. Let's look over it again. That was one big slide. So let me tell you. To look out for. Okay. Yeah, so it's going to be a double pulley problem with the same logic that we have here. So the picture, you have the problem set up for you. Perspective is just going to be the vertical axis, y-axis. The system, will be moving towards the right, or whatever the case may be. You just determine what the system is. The side that has the larger mass is going to be moving downward, and that's the direction of the acceleration. After your perspective, draw your free body diagrams for all masses. Once you've done that correctly, then step 3, you write down your equations of motion for all of the masses. So we have, in this case, we have equation for mass 1, 2, and 3, all of the forces attached to those masses, and you can see that the tensions can cancel out. That helps you solve for one variable, and you can back substitute and solve for the other ones. Which is what we did. Yes, step 2 is just the free bodies, if you will. So Yep. So I wanted to have it all in one part there. Step 1 is just the perspective, just making sure that you understand how the system is moving. So step 1 is like, instead of just like y and x as we've had before with normal force and an object moving down a ramp, or if we had friction on a horizontal surface, it's just going to be moving vertically. So that's all the perspective that you need to have in a pulley problem. It's always going to be vertical. Well, in this type of pulley, because you have a pulley like we had in the homework, we had horizontal and vertical. Like if we have a pulley at the end of a table, and we can have a mass hanging off of the end of a table, pulling a mass that's on the table. So yeah, so get your perspective first, draw your free body diagrams and your equations, solve. Yep, that's pretty much it. So there's one thing I'll seek to do with any type of problem is to make sure that you understand the method that's necessary to solve the problem, because that's going to be, half the battle in getting things solved. And when you know what to do, you know why you have to do it, and that's all understanding the methodology. Okay. If there's no further questions, that can do it. So yeah, we have the homework that's due today. You turn that in 5 o'clock. So like I said, so the next class tomorrow, we'll have this to be maybe the last 30 minutes of class, your skills test. You can talk about a couple of things before, a couple of homework problems or whatever the case may be. So anything else? No, I'm actually going to be having at 1 o'clock, I have a session with my regular class. So any makeups, you guys got to show up. Skills test makeups are going to be during my office hour in the mornings, every Wednesday mornings, from 8 to 8:50. We can do that tomorrow. Yes, Nicole. Yeah. Yeah, no problem. We could probably do both of them. Yeah, that should be fine. Your 10-week. We could do that. We'll probably do that next Monday. Your 10-week your 10-week exam makeup. Okay.